Thank you. So today I'm speaking about I think the accurate word is not survey. It's more like a tick report that we are looking at. Our perspective is moving to PostK, and many parties are involved in that report, from Tokitech, from AIST and Tokitech AIST, Open Innovation Laboratory, and also RIKEN itself. Why this report to begin with? It all started from a question by Professor Matsuoka, and he's director of RIKEN CCS. So he asked a very simple question, which is, what is the path forward and also the effort required to qualify PostK for supporting deep learning software stacks? So we gathered and we thought that we should have some fundamental conditions or like assumptions here that we cannot negotiate. First one is that we assume that PostK must support training deep neural network and not just inference. I think that's a given thing that we are not negotiating. And the second is we assume also no branching or like hard branching or custom version of deep learning frameworks. So we assume that we don't want the users coming on to the like PostK to be locked to a custom version of some framework or a new framework that we will have to maintain, all the people at RIKEN would have to maintain, but we assume it would be a seamless process in which if a user has been using a framework for some time, he would seamlessly move to PostK. So those are the baseline assumptions and those are the goals. So moving towards or those two goals, what exactly is the effort required? So I begin with a summary. Like the issue is not just a low primitive library. One would assume that if you have a low level primitive library that interfaces you with hardware, it just would be enough. But the question lies is, from the deep learning frameworks out there, how would we interface that? Since we discovered that the deep learning frameworks have like are designed differently, meaning that there are different trade-offs taken by the developers of these frameworks with respect to supporting new hardware. So this is something we have to consider. So again, not just a primitive library, but how to make it work assuming it exists. And it doesn't exist as we speak, of course, for PostK. One thing we found is TensorFlow, which is something we looked at very closely since it's one of the most commonly used, if not the commonly used frameworks. It's modular. It's relatively easy. Since defining and interfacing new backends is relatively straightforward. I'm not saying it's a small amount of work, but at least this is straightforward. Another framework we looked at closely is called Chainer. I'll explain later in the slides. It's a commonly used framework in Japan. I wouldn't say it's as modular as TensorFlow. It has a small code base, so you can assume that you can add some support for it with a hackish way, let's say. And we also looked at the model exchange frameworks, Onyx and NNEF. They do not support training in the currently, but they might support training in the future, so that's why we looked at them. So this was a summary, actually. So what was the survey methodology? So one thing we started first is that we want to investigate deep learning software solutions at different levels of abstractions, essentially. We use an automated approach. Essentially what we did is we used basic DNN primitives. So we define very small pieces of code, let's say use an activation letter or activation function, or just multiply two tensors together. And then we would trace the execution paths and also the call stacks. And as we go through that, we try to collect code fragments, and we focus actually on cases where we're using CPU and GPU, since most common frameworks now support CPU and GPUs, and try to see where are different execution passes. Knowing these different execution passes, that can give us insight about where exactly we have to change and how much effort is required if we are to add a new target. So this was the methodology. Of course, for the sake of time, I'm not including any code samples or any code to appear on the screen, but in the report, there's a lot of code, and we describe this method in detail. So the scope is, the objective is actually to looking at survey for ARM CPU platform, and to be more specific, the ARM variant that we would have in PostK. One would think that to do that, we should look at current existing frameworks, look at this report for CPU. This will give us an insight what we need to do exactly as we move to ARM, the PostK chip, since it's also a CPU chip. However, we realize that frameworks are not really thoroughly optimized for CPU as they stand, and that stands for all frameworks actually. That's because some frameworks are not optimized at all for CPU, and that's because there are very heavy emphasis on using GPU by frameworks that most of the backends for CPUs are not up to the level optimization of GPU. Hence, we decided not just to focus on the CPU backend, but also on the GPU backend to study them and try to understand more. So this is an overview of like deep learning software stacks. They have minor differences, but in the end, they all have 3 layers: front end, an intermediate layer, and then a back end. So for the user interface, you have 2 things you can concern yourself about: the API that you use as a user. And in this study, this is not really the focus, because we really want to focus on supporting the back end while preserving the APIs as they stand. Because again, like in the first slide, we assume no customization or something like that. And also something that belongs to the front end is importing and exportation of formats. I will come to details about that later, but this allows you to move between frameworks. Then you have a layer of abstraction in all frameworks, which is an intermediate representation. In most of them, it's a graph level optimization. They have different philosophies in looking at some look at it as a like graphs you would execute directly, and some look as a graph just at a description. You cannot execute, but it gives you just a description about that. And then you have the backend, which is a tensor computation. And some are hard-coded inside the code. Some use code generation to generate code to your backend. Some have a deep learning primitive library, and this is actually the most common you would see, something like cuDNN or Mkl Union. And some would just use directly BLAS. So those are like the layers. In our study or our report, we looked at all levels of these layers because we're concerned not just at the back end, as I said before, but also how to interface and make sure that we seamlessly move to PostgreSQL with minimal friction as possible. Friction, sorry. No. So first, a little word about model exchange format and why they are relevant as we speak here, because you might think model exchange format is something at a higher level. Why care if we're speaking about a new backend, the chip we have in the new PostgreSQL? Well, it's important because it allows you to move between frameworks. So one might think that pragmatically, you might think that if I support one framework or a backend, then I might be able to allow users to use different frameworks and then use exchange formats to move between frameworks seamlessly. So one would use a framework to develop his work, and then while he wants to execute, he would use an exchange of format. So we think this is relevant. It's getting more traction in the deep learning community. Started out as a way just to exchange formats, but now it's getting more and more functionality that we can see at one point, like seamless motion between them. As they stand, there are 2 common ones or more spoken about. The more common one, which is ONNX, Open Neural Network Exchange. It's an extensible graph computation model. So you represent, when you exchange, when you export from one model, you create a graph essentially. It's an executable graph. And then you can take it to another model. It's also a rich, actually, format representation, given that it gives you built-in operators and data types. It has some limitation that no cycles allowed, which means in some types of models, like recurrent neural network, it would be an issue. Must adhere to like single static assignment. Only this layout, which is supported, but we think as people now have moved to NHWC, which is a different layout, we think this is not an issue. People can move on to new layouts, and no back propagation, which means that it's for inference as it stands. Another less commonly used format, which is much more simpler in the sense that when you present your model, it's in a graph that's not executable as in ONNX and ONNX, and it's not as rich actually, but we thought it's worth a mention. Also, we studied it a little bit. As it stands, ONNX, this is from October 2018. These are the frameworks. As you see, most frameworks are exporting. Some allow importing. And we expect as we move forward, there's more exporting and importing that can happen for ONNX. So I think this is a valid thing people should look at. Next thing I speak about, remember the 3 levels we had, the interface. When we had the top layer, we spoke about the model exchange. And then we're speaking as the lower layer now, the deep learning libraries for primitives. So one can go to a first order approximation and say, you know, deep learning is just BLAS. Why not use BLAS primitives? Well, you can do that on a new chip, but then it doesn't become HPC, just C, just computation, because you do not guarantee the highest performance. And as we seek highest performance, then just using BLAS, raw BLAS as it stands is not enough, because there are often like more efficient specialized algorithms used for this type of computation. While the algorithms are common to the deep learning frameworks, for example, like GIM-based, FFT, Winograd, and such, but the implementation is hardware specific. That's why it's not a coincidence that the libraries are typically developed and maintained by the hardware vendor. So the most common library, cuDNN, is developed and maintained by NVIDIA. You have another library for Intel. There's one for ARM, and so on. While this part of the puzzle needs to exist for PostK, as it stands, it's not clear yet how we approach that. I believe there are a lot of efforts being done. I think Matsuoka and Steve will probably speak about that tomorrow. But then this is a part that it's very crucial. And like we mentioned, it's just not enough to have BLAST. It has to have some native support to guarantee the highest performance. So we speak briefly about 3 of these primitives because we think they're important. In the report, we did actually like code trace, trying to understand as much as possible. The most commonly used one, that the name is synonymous actually, is deep learning, and this is due to very heavy marketing from NVIDIA, which is cuDNN. It's a closed source library. It provides primitives for DNN that includes backpropagation, so it means you can use for training, like you can have n-dimensional convolutions, pooling, activation functions, softmax, tensor transformations, normalization, RNN, and etc. It includes up to 8 different convolution algorithms you can choose between. And there is work, even like in Matsuoka-sensei's lab, that shows that you can wisely choose between different algorithms for different types of tensors. It gives you different results. And actually, this is some observation that is very recent, like we're speaking in the last few months, is cuDNN is starting to evolve to allow fusing some of these operators. So for example, you can fuse batch norm with add and ReLU operations, which means that cuDNN, it might be a direction where cuDNN is not just a primitive library you call, but you can actually do some more high-level semantics to fuse operations and such and drive your execution. Another one that we're looking at is Mkl Union, which is by Intel. It's open source, yet if you look closely, it relies heavily on MKL, mass kernel library, which is closed source. So essentially, it's closed source. At the performance critical parts of it, it's closed source. It supports many primitives, so like not as rich as cuDNN, but still supports most of the primitives in cuDNN. It supports both x86 and Xeon most primitives are FP32. Some also are int8. And there is no mention of reduced precision training, which is supported by cuDNN. I think it's not so clear 100% now if mixed precision or reduced precision training will remain to stay, but as it stands, it's not in Mkl DNN now. Why we looked at Mkl DNN? Because one would think it's a rough proxy for the effort required. So whatever was introduced in Mkl DNN would probably be somehow a rough proxy as to what you would need in PostK. It has about 80,000 lines of code, yet it has support for FP32 only, so we might need more. But also it has a range of processors with different like AVVX and different types like ISAs from Intel. So it has a very bloated code base. So I think if we reduce it, it's up like about 30,000 lines of code to support Intel backend. The one we looked at, ARM NN SDK, it's open source. It currently has support for Caffe. And as it says on the website, TensorFlow, but I think it's not complete yet. Maybe I'm out of date my information, but I think it's not complete. It supports ARM Cortex CPUs and Mali GPUs, so it has CPUs and GPU support. However, one main point to mention here is that it's a forward propagation only. So it's not usable as it stands. Because like we said, the main crucial part is that we need training in PostK. There is no way to derive backward computation because models are read from something called prototext format. And this represents the computation graph, but as it stands, we try to see if we can use this format to do some form of backpropagation, extract the information, but as it stands, we were not able to do that. It's a smaller library versus the one Mkl DNN, which is understood because it only supports forward propagation inference, because this is the main concern for ARM. It has about 21,000 line of codes. It heavily relies on C++ templating. So now I'll speak a little bit about 2 frameworks we looked at. We looked at more than that. We looked also at Caffe. We looked at other stuff, but we focus on these 2 more because one of them, for political reasons, is heavily used in Japan. So there's a big user base. So we want naturally to look at it as a prime candidate to support on PostK. The other, which is speak about here, is TensorFlow, because again, it's commonly used. So Chainer, if you're not aware of it, it's a Python-based framework that's widely used in Japan. It's heavily geared from day one towards GPUs, and it's a define by run approach. And this is one of the 2 approaches that exist for models. If you look at the stack they use, you can immediately identify it's not modular, in the sense that if you want to use Mkl DNN, it takes a different path versus CUDA, because if you use CUDA, you have a library called CuPy, which is think of it as NumPy, but for GPUs. But for Mkl Union, they internally define something called IDEEP. So you end up with a not so modular implementation that's really hard coded. So to give you a mental image, think of FDEF style of programming. If this, do this, if not, do that, which is not really the best of way when you want to extend work. It uses also one interesting thing, it uses NumPy as container for Tensor, unlike TensorFlow, which uses a proprietary Tensor format. You have to format your arrays first into their format, the tensors first. And in distributed training, it uses like MPI, called chainer MN, plus Mkl, NVIDIA Mkl if possible, and the intranode level. So it's a hierarchical approach. However, like Chainer has just announced very recently, actually a couple of months ago, something called Chainer X, which is a new variant that is modular, that fixes some of the issues we spoke about. It's not clear if it will replace Chainer or not, or if it will be a standalone like a library, or if it will like merge. It's not so clear up to now. But as you move from Chainer to Chainer X on the right, you start to see that you have like a more cleaner interface that Chainer hides the backend. So you would have native backend, you have a CUDA backend, a custom backend, which should, for example, be PostgreSQL or something like that. So this is a much cleaner interface that separates the front end from the back end. So you don't have to concern yourself with FDEF programming all the way up from the front end. So this is Chainer. Again, the report has a lot of studies on that and code samples and how we traced, but for sake of time, I will not speak about that. TensorFlow, it's a much more widely used library worldwide, Japan and outside. Actually, it's a symbolic mass library for tensor computation. So it's not, strictly speaking, it's not a deep learning framework in the easy fuse. And it has different front ends and different back ends, even for mobiles, actually. For the front end now, more and more, there was a Keras, which is essentially a front end, commonly used front end, that makes it very easy to use in the sense that it looks like Chain or others. But very recently, Google announced that it will be the official Python front end. It also most notably includes something called XLA, which is I think it's a beta version or alpha version actually, compiler for linear algebra. So think of it as that you have two options. You can use TensorFlow, in which you have a front end for different languages. You have the execution engine, which is intermediate representation. Then you have the backends, or you can use something called XLA, which is a compiler for linear algebra. It's very strong. Think of it as a LLVM, but for deep learning, that you have an intermediate representation and you can do optimization passes. So rather than in this side, in which you would typically have a graph, but the graph, which represents the nodes, represents computational parts, are pre-compiled, and you just drag them along and place them somewhere to be executed. In XLA, you can actually jet, compile, and generate those computational parts. So this gives you a lot of strengths, because now you can generate whatever you want for the back end you have. So this is one direction. If you want to create a new backend or support for PostgreSQL or any other processor, to go this way or that way. However, problem with XLA as it stands, like I said, I think it's a alpha version or a beta version, and it's not clear if it will stay or not, if Google will push it to be part of the main body of TensorFlow. So it's not something very reliable to rely on for the future. However, it's a very strong tool. So to think of TensorFlow, how would you? It doesn't just allow you to extend the back end, but also the front end. So in the front end, let's say deep learning in computational science starts to see some very new exotic types of operations that you would want to use. So not just the back end, so also the front end. So it allows you to define and add something called operators. And then the TensorFlow can make a graph with these new operators. It's relatively easy and straightforward, yet it requires some knowledge of the internal C++ code used. Also extending the back end, the user has to define how the graph is executed. So when you extend the back end, it's not just that you interface it with a primitive library, but also you have to dictate how to use the graph. And this is very important, because look, for example, at the Fujitsu chip, as mentioned by Professor Ishikawa in the previous presentation, in which you see that the processor has 4 CMGs. So ideally, if you have a graph, you would want to split it so that you maintain high data reuse and locality. So this is something that if you would want to support the back end in TensorFlow, you'd have to look at, again, not just the primitive library, but also how to interface and how to partition this graph into subgraphs in an optimal way. For distributed training, it uses something called gRPC, Google Remote Procedure Call. There is an MP version that exists since gRPC has scaling issues, yet as you see in the deep learning community, despite the scaling issues, people are still heavily using gRPC. And very recently, which is a very interesting thing, they released something called Mesh Tensorflow, model parallelism. Model parallelism has been introduced very early on, but I think it was premature. I think it's having a comeback again for model and hybrid parallelism, since we start to see bigger and bigger models and bigger input data sets. Because in scientific computing, you can have like if you have like medical imaging or some application like this with very deep channels, you might end up with very sample size that essentially the like actually just one sample. In that case, like model parallelism and hybrid parallelism are becoming. So this is also an interesting thing that we're starting to look at. I will skip this for sake of details and go directly to summary, which was the first slide, essentially. Like mentioned, the issue is not just a low primitive library. This is something that's required by all means. And it's important to know how to interface it. Different frameworks are designed differently. Today, I just spoke a little bit briefly about Chainer and TensorFlow, but also in Caffe and other frameworks you looked at, there are also other like different design trade-offs, how to interface this lower level primitive. TensorFlow, as we spoke out, was more modular, and I think defining and using a new backend is relatively straightforward. It's not easy, but it's straightforward at least. Chainer does not have that at a stance, not Chainer X, but Chainer, the main thing, does not provide this separation of concern, yet it's a small sample code, so you can still hack your way through it or go with Chainer X if you want. And the model exchange format, I think, is something that's very interesting to look at, because it might be a pragmatic choice to choose to support these formats and then have a back end and interface for one of these frameworks, and then rely on the providing the capability for users to use these exchange formats. Things I did not include in that is I/O and more deep study of training, like the communication essentially. We had some communication results on K, where we looked at TOEFL 2. Results are very outstanding, and I think Matsuoka Sensei will probably have some slides about that tomorrow. And we expect it also. And also very lately, I've been also looking at I/O, since I/O is becoming a real issue when you look at real production systems. Report is in its final touches for like have official release. We will include the I/O part, early stuff about it, and the like communication part, and release it at large so it gets traction. And we'll have it open also. Somebody wants to add to it, so maybe this is the right platform, I think, to discuss such an issue. And with that, I conclude, and I thank you.
Thank you. Any question, please?
Thank you very much. Do you have any, this is related to the last part of your talk, and do you have any, there are pre-performance evaluation about the interconnection issues for the deep learning on the post-K? So there, because some people say that deep learning, large-scale deep learning is not just the same, like an ordinary HPC application, so the network pressure is relatively low. So how do you expect? So you mean that the ABCI has just a half of the performance of the interconnection, for example, compared with your Tsunami 3?
Yeah. So I'll talk about it tomorrow, but in data parallelism, there's significant demand to basically exchange the activations, because you have to do the average sum. And what's the difference between the normal HPC workload and also the deep learning workload? The normal HPC workloads are usually latency bound, where because payload, if you look at the payload side, this is a work from NERSC about 2010, 2011 timeframe, when they did a survey. They found that the average payload size was 8 kilobytes to 32 kilobytes. So obviously, it's very latency bound. It's increasingly becoming latency bound as the network becomes faster. But for the data, especially for data parallelism, as Wahib pointed out, basically the data set's getting bigger and bigger, and thus every time you do or you try to enlarge the batch size to the maximum that fits in the memory, then for any sort of activation, that is all the gradient information has to be set, and these are basically throughput bound. And we found in our performance models that actually it does affect performance. Now for ABCI, I'll talk about it was a compromise. So but for on the post K, on a K computer, we have done benchmark, and it scales just beautifully to nearly 88,000 nodes. So we have pretty good confidence in the post K. This will scale to more than 100,000 nodes if needed. And the deep learning training with respect to data parallelism, in terms of exchanging data, will be less of an issue, as opposed to the another problem, which is handling very large batch sizes, which affects the convergence. But we're working on that too, and we have a latest paper on that, using a quadratic optimization.
Thank you.
Thanks for your introductions. So I'm curious about two issues in your talk. So when you're fusing two operators or define a new operators, if you don't have an implementation in your library for such custom operators, how do you deploy and improve the performance of such operators? And
Okay.
the second question is, have you ever thought about developing your own domain-specific frameworks, maybe like TVM or tensor comprehensions developed in Facebook or something like this?
Okay.
Thank you.
Okay, thank you. So for first question is about fusing layers and such. So for existing stuff, like I gave an example, Mkl Union, since they allow you to fuse, so they give you the capability to physically fuse. So they have backends that allows JIT compiling and producing. There's a lot of body of research recently, and actually I'm working on one of this, was one of the PhD students we have on how to do this fusion properly. So one way to look at it is that you don't necessarily have to have custom versions. You can start to have source-to-source translation or JIT compile these fused new operators. This is like a meta level.
Do you have your own source-to-source translator?
We are experimenting, but this is research level, like academic stuff, so it's not really production. If it's something that it's worthwhile, then maybe you would naturally. I think the pragmatic choice is to try to have pull requests with any of these frameworks, trying to have support for it. But to walk alone and say I have something and everybody must use it is not so realistic. This actually answers the second part of the question, which is having your custom thing. You can always customize. And it's always easy to say, hey, I have my own target, I know my own requirements, and I go for that. But I have to remember that PostgreSQL is a public utility, just as any large system. And you want to have if you would go with customization, you'd have custom hardware from the beginning. But you want to have like the common denominator for all users. And you want to attract users who are already using deep learning, because when this machine is online 2021, 22, I'm not sure, that's by that time you expect already to have codes that have been using deep learning. Like Matsuoka Sensei mentioned, the mission critical application are already looking at that. So it's not so realistic to tell them after that, hey, you have a custom solution, you have to look at it. That's why the more pragmatic and realistic thing is try to have minimal friction as possible and migrate users